My colleague Ian Lanius is here. He is an exhibitions preparator, and he and I are going to talk about photogrammetry and how you would create 3D models from photographs. Now, I am going to, if I can get back to the chat screen here, see if I can do that. There we go. I'm going to share a link in the chat. And this is to a box folder that contains materials that we will use at the end of the session for a hands-on demonstration using an application called Regard 3D. The installation files for the software, either on Mac or Windows, are included in that box folder, as well as a set of photographs that we'll use as a demonstration project. I just wanted to share that now in case you're interested in downloading those materials. You'll have plenty of time to get those things ready before we're actually at the point where we're going to need them. So the outline of our talk today, we're going to first discuss what photogrammetry is and a little bit of an example, a couple of examples of applications for that technology. We'll talk about structure from motion, the John Ezell project, which is a project that the libraries are involved in right now using that technology. And then we're going to end with a hands-on demonstration with Regard 3D, as well as then a period to wrap it up and allow you guys to ask questions if you have any. So with that, I'll get started. What is photogrammetry and how is it used? So photogrammetry, as defined by the American Society for Photogrammetry and Remote Sensing, is the science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring, and interpreting photographic images and patterns of electromagnetic radiant imagery and other phenomena. And so that's a very wordy definition, but I think it captures exactly what we're talking about here. But to summarize, we're basically talking about correcting spatial distortion in photographs. And this is the this was the initial usage for photogrammetry. A lot of aerial images were collected in particular for usage in the defense industry, and they wanted to make measurements from these photographs. And so they devised some methodologies for correcting that spatial distortion that would allow the preparation of topographic maps, digital elevation models, and orthophotographs. And these are items that you could actually take accurate measurements from as far as distances, heights, areas, and in 3D, we can measure volumes. And the newer or more modern usage of this technology is to extract 3D data from 2D images using a process that's also known as structure from motion. And this technology, this methodology has some key applications in mapping, archaeology, and now in the 3D modeling, not only of topography, but also of other features and objects that might occur in the landscape. So the whole point here is we're going to convert images into 3D objects. And the process involves the capture of multiple overlapping images. And the figure that you're looking at here is just a cartoon describing the boxes that you see in the sky above the ground plane there represent images that would be captured at those specific locations using a camera in an airborne vehicle of some kind. On the ground, we would identify specific tie points that would be visible in all of those images, so that the images themselves could be stitched together into a mosaic. The ground control points are actually points of known location. So we have very detailed and accurate information about the X and Y and sometimes Z values of those points. And those are used to georeference the image or the digital elevation model or whatever product that we're generating from this process. So the whole point is we're going to align and mosaic these images, and then using an elevation model, we can correct for spatial distortion and then create a three-dimensional model. So An ortho image is basically a top-down view of the Earth, and it allows for accurate measurements. This is an image from Space Imaging, and they use it to advertise what they called a true ortho image. In the image on the left-hand side, you can actually see down the sides of some of these buildings because they're off nadir, or in other words, they're not underneath the optical axis of the image collection device. And so we can actually see down the sides. This company basically developed a methodology for stitching multiple photographs together so that we can still see a nadir view basically at any point in this image. And the idea is it's removing that distortion. As you can see on the right-hand side, we can still see the shadows extended from the buildings, but we don't see down the sides of those buildings anymore. And this was a product that they were advertising and selling to the Defense Department. So there are several different image collection methods that we can use for photogrammetry. In some cases, we're interested in large areas. And so the collection devices in those cases might be airplanes, helicopters, small planes, and in some cases, drones. If you attended Alex Bradley's talk on Thursday, he talked extensively about using drone platforms to collect images and other types of information that could then be used for analysis and modeling. So these sorts of platforms, these aerial platforms, allow us to collect information over a relatively large area, and that would allow us to create models of larger features. We can also use the same technology and the same concepts to collect information on smaller objects. And that's really the subject of our talk today. So the terrestrial or smaller objects can be collected in the instance on the lower right by a drone that's maybe orbiting, in this case, a barn or some building feature on the ground, and taking multiple photographs from various angles. And Ian's going to talk a little bit more about that particular process here in a moment. But we can also devise these constructed environments where we can capture a lot of photographs at the same time. The man on the left-hand side of your screen is standing in the middle of a network of cameras that allow the simultaneous collection of images of whatever object has been focused in the middle section there. And so in one instance, you can create and capture photographs from every angle of that of the object that's in the center of that. Now, the person at the upper right, he is using a turntable to actually capture using a static camera to capture multiple angles of images of this particular object, in this case, a small sculpture of an elephant. And so in that case, the turntable will move, the object will turn, and then the camera will be used to capture several different images of that to hopefully capture all angles and then allow a proper model to be developed. Now, these are various methods of capturing these images, but what would we actually use them for? So there are several different applications I'll talk about. One of them is a company or a nonprofit called SciArc. And this is an organization that was founded in 2003, and their mission is to digitally record, archive, and share the world's most significant cultural heritage. And in this image, we can see several examples of the work that they've done. The Mount Rushmore project I would call out as being particularly interested. They obtained access to that monument and were able to capture close-up imagery. They actually had access to the monument itself. They were able to climb and position cameras and scanners and so forth to capture very detailed digital information about the monument that allowed them then to construct a 3D model of that particular monument. And they use this sort of practice at various places to capture either areas and facilities that might be difficult for people to get to, or facilities that may be dangerous to allow the public to have access to. And in some cases, they've done this to capture and document or an area or a cultural heritage site that might then become damaged in war or some other event. And so it allows us to preserve and provide access to these cultural sites. Another group that I'd like to call attention to is the Cultural Heritage Imaging Group. This is another nonprofit out in San Francisco. And this group is basically involved in training preservation staff and others interested in capturing and preserving this sort of information to perform the photogrammetry process that we're going to be talking about today. And in the example images that you see here, this is from a course that they provide. It's a 4-day course on this practice that gives people hands-on experience capturing the photographs and then doing the processing that would be required to produce a 3D model that you can see on the right, which is a model that's been shared through the SketchFab site of an Olmec colossal head. And so they capture photographs of the object on the left, create a 3D model on the right, and we'll see an example of this later. The SketchFab environment allows a user to basically pan and zoom and rotate around a 3-dimensional object, and it gives someone a much more immersive and interactive experience with that object through a browser. Now, we also have a local example of utilizing photogrammetry technology for educational purposes. So the Fawcett Lab in Earth and Planetary Sciences uses this technology to create 3D virtual field trips and to visualize complex objects such as the crystal lattice structures that you can see the students all looking at on the right-hand side of this image. On the left-hand side, Phil Skemmer and Martin Pratt are viewing a shared 3D model utilizing Microsoft HoloLens headsets. And so they've basically built a hologram of a geologic feature that they've displayed inside the Fawcett Lab facility. And they are wearing HoloLens headsets that are synced up. And so both of them are able to visualize and see the exact same object, and it's indexed into the same location so that Martin, in this example, is pointing at a location. Phil can see this in his headset, and even though the object that we see in that image isn't actually present in the room, they are both able to interact with it, and it can be used as a learning tool and to provide several experiences that might be difficult or require an expensive field trip to expose students to such areas. Now, one more thing I would like to point out is the use of this photogrammetry technology to share hidden collections. And that's kind of the example that we're going to be talking about today. But I wanted to post this slide because it shows some images of collections at the Smithsonian Institution that are basically not available for the public to view. And so the collection is so large and extensive that it's very difficult for them to share access to all of this material through their exhibition spaces. And the image on the right-hand side of the space shuttle, that's a very difficult object to move around, and it might be nice to be able to allow people access to it. And so they have done in their 3D digitization group, they have done a lot of very extensive image collection and then photogrammetry to create 3-dimensional models that they can then share through the web for educational purposes and to give people more access to their specific collections. And with that, we're going to move on to the structure for motion section, and I'm going to turn it over to Ian now. Ian, I'll let you take it from here.
Thanks, Bill. My name is Ian Lanius. I'm, as Bill said, the exhibitions preparator in special collections. We create exhibitions in public spaces all through the library that are open to the public. So I would encourage you all to check those out. My background is in fine arts. I studied photography and video art. And I've always been interested in, you know, for lack of a better term, high-tech tools in photography, and that's how I've approached this project. You can go ahead and go to the next. Yeah. Okay, so structure for motion, here's the Wikipedia definition. A photogrammetric range imaging technique for estimating three-dimensional structures from two-dimensional image sequences. And that basically means you feed software a large amount of still photos, and it does its magic to give you a 3D model. And one of the things that I find so powerful from my perspective with structure for motion compared to other modeling technologies such as LiDAR or structured light scanning is that the hardware required is accessible to just about anybody. Up at the top here, there's a picture of a drone. This is the drone that Alex Bradley and his team used for a project at Johnson Shut-in State Park. Below there, you can see a drone that's sitting in my hand, and you can probably guess which one is more expensive. The structured light scanning requires a video projector, a couple specialized cameras, and structure for motion. You can really use any modern digital camera to get really good results. You know, you see I've got a picture of an iPhone there. You don't need an iPhone Pro. You know, really any digital camera that gives you a decent resolution will give you really good results from structure for motion system. A drone is handy if you want to do something large, you know. For that colossal head, and a few slides back, you can see they had a camera on a pole to get on top of that. But, you know, if you want an architectural site or an archaeological site, or, you know, a building, what I mean to say is the camera on the drone that I have, you know, this picture here that I bought for a few $100s is really no different than the camera in your smartphone. The only reason it costs more is because it's attached to an aircraft. So really any camera you can do this with. And it's exciting for me that the power of this technique is in the software, which, as you'll see later, can be accessed through open source applications and not specialized hardware. The barrier for entry is very low. You can go on to the next slide. So, you know, like I said, I come from a fine arts background, so I'm certainly not going to get into the technical details of the algorithms used in structure for motion, but it relies on kind of the most basic principles of visual perception, specifically motion parallax, which everybody knows. You know, as you can see in this little GIF, you might not know the name of it, but it's the principle that when you move things in the distance, because of foreshortening, things in the distance appear to move slower than things closer to you. And this is something, like I said, it's just foundational to our perception of the world visually. I can remember one of my first memories, in fact, this is a true story, was riding in the car with my mom. And I noticed, you know, we're driving past buildings, we're driving past cars. And I asked her, why don't we ever drive past the moon? You know, we never pass the moon. The moon's always in the same spot. Why don't we pass up the moon? And, you know, she didn't say, oh, that's motion parallax. She said, well, the moon's far away. But that's basically how the software, and, you know, in fact, how our eyes judge depth. You know, we have stereoscopic vision. So we've got two viewpoints. And I'll also mention that our stereoscopic vision has lots and lots of overlap, which is important for determining depth. And with structure for motion, we're basically, you know, we can get pretty basic depth information from our 2 eyes. But if we had many, many more eyes positioned in many different positions, you can imagine our brains could create more detailed models, and that's what the software does. You can go ahead to the next slide. So yeah, at first glance, it seems like, how do we get 3D from 2D? And so one photograph has 2 dimensions, but to collect these many photographs, we're moving through 3 dimensions. And even though each individual photograph only has 2D data, the software, through comparing points and knowing about parallax, can build depth information. And I always remember when I'm working with photogrammetry, my video art instructor would always tell us, video is not a 2-dimensional medium. Video is 3D. You've got 2 visual dimensions and then the dimension of time. And I always think about that when I'm collecting multiple images. In fact, there's a connection in fine arts between video art and sculpture that I relate to this type of work. And the reason why I have this chimpanzee holding a Rubik's Cube is to exemplify that the software uses really the most basic sort of instinctual ways that all animals experience 3D space. If you give a chimpanzee an object, or in fact, if you give a human an object, the first thing they'll do is move it around in their hands to kind of see it from all angles. If you put a dog in a room, they will look around. If you put a human in a house that they want to buy, they're gonna basically collect the same type of data with their eyes that you would with a drone if you wanted to build a model of it. It's really foundational principles of perception that are being put to work through software. Go ahead to the next slide. So I'll talk very briefly about capturing images here. I'll go into that more specifically when I talk about the Ezell project. But like I said, good data requires lots of overlap between images because the software wants to see common points between images on an object, but it wants to see a different background behind those points. Like use parallax to find out how far away the stuff in the background is. You want to have everything in focus. With a drone, pretty much everything you shoot will be in focus. With the camera on a drone or a smartphone for that matter, pretty much everything beyond, 10 feet is all going to be in focus, just because of how the lens is set up. If you shoot smaller objects that are closer to the camera, then you have to consider depth of field a little bit more. I'll talk more about that later. And more resolution is better. The more pixels you've got, the better the software is going to work. There are other considerations for image clarity, like physical sensor size. And depending on the amount of light you have, there's kind of a trade-off for that. I'll talk a little bit more about that later, but in general, more resolution is better. You can go ahead and go on. So yeah, specifically about the John Ezell project. And actually, I was remembering recently that the birth of this project was the very first exhibition that we showed in the Thomas Gallery in the library featured some John Ezell maquettes. And Jennifer Moore, the head of data services, and full disclosure is also my wife, she said to me, we should make 3D models of these. And here we are, years later. You can go ahead to the next slide. So the way special collections works, before I was in the exhibitions department, I was a curatorial assistant, and I worked in the special collections reading room. which is the place you have to go if you want to access these collections. And Bill talked about hidden collections. Pretty much all the special collections are hidden collections. One of the reasons when we expanded our exhibitions department here at the library that I wanted to work in that area is that it's the portal. I see these exhibitions as a portal into the reading room to get more in depth. You know, I grew up in the St. Louis area, lower middle class. My dad took me to all the museums in the area because they were free. And I loved it, but I never considered going to the special collections reading room. And when I started working in there and realized that we were open to the public, and in spite of that, the only people that came in were scholars, you know, either students at WashU or, you know, a doctoral candidate from Princeton might come in for the summer. And it was really frustrating that more people couldn't see the stuff that was super interesting, this museum level stuff that you can actually touch, you know. So I'm really passionate about making these collections more accessible. And, you know, I really found one of the biggest barriers to getting people in that reading room is the parking. You know, that's just an aside. But like I say, I'm really passionate about opening access to these collections because they're really the coolest stuff the library has. And this collection in particular, I think it's about 40 maquettes. There are other collages and other materials in Ezell's collection. And when I first toured the vault that these are housed in, you know, I was amazed. I was like, wow, I want to see more of these. They're, you know, if you think about the dioramas that you made in grade school, it's like extremely technically proficient versions of that. It's like, you know, at the highest level, they're really beautiful. And they're also really useful for people that want to go into stage production or sculpture, you know. So anyway, we can go on to the next slide. So yeah, here are some examples of some of the models that we've made from the maquette in that last slide. You can go ahead. So yeah, now I will talk a little bit more about the specific considerations that we've had for the photography of these maquettes. You can go to the next slide. So I want to talk a little bit about basic photographic principles. With a digital camera, there are 3 variables to get correct exposure: aperture, shutter speed, ISO. Aperture is just the size of the hole in the lens that lets the light in. Shutter speed is the amount of time that light is let into the lens, and ISO is the sensitivity of the photo sensor, or, you know, film if you're using a film camera. In the old days, you would have to pick a speed of film, and then you were stuck with that for 36 frames. But luckily, with digital cameras, we can change that whenever we want, as an equal parameter to aperture and shutter speed. So you can go to the next slide. The main consideration for shooting these relatively small objects that are close to the camera's depth of field. You know, you can see deep depth of field, many things in the frame are in focus. Shallow depth of field, really good for wedding photography or portraiture, really bad for photogrammetry. So a smaller aperture gives you greater depth of field, and a smaller aperture is a larger number in f-stops, which, you know, it's just how it is. And the way I remember this is like, if you squint your eyes, you can see more things in focus. So it's a good little mnemonic device for that. That smaller hole gives you greater depth of field. You can go to the next slide. So in the studio, we can control the light really well, which helps us. So we can use the lowest ISO. The native ISO of the camera is 100, which is the least sensitive, but it gives us the least noise. Or in the film world, you know, you would think of noise as grain. but on a digital sensor, it's called noise. So the smoothest tones come from using a low ISO. And because we have as much light as we want, and because we have the camera on a tripod, we can do that. And because we have the camera on the tripod, we can use whatever shutter speed we need. Between that and the fact that our object is not in motion, we could take a picture with the shutter open for 10 seconds, and we will have no motion blur because we have a tripod and a table for the object. When you're out in the field, say you're shooting a landscape that has trees that are waving in the breeze, you might want to use a higher shutter speed so you don't get that motion blur. But in the studio, we don't have to worry about, which leaves aperture as the thing, and that's what we want to control. Because these are relatively small objects, we want to make sure everything is in focus. Because if there are areas out of focus, like those wedding portraits, the software can't grab onto that. It needs detail, it needs edges and sharpness. So the main consideration in shooting these models is using an aperture that's small enough to get everything in focus. And we're also using a mirrorless camera that has a relatively large image sensor, which also helps to reduce noise, which is not, like I said, it's not probably the least important factor in this, but everything helps to get good, sharp, clear images. You can go ahead. Oh, and back to you, Bill.
Okay, and back to me. And actually, I'm going to back up just a second because I wanted to highlight something in this image that you can see Ian and I here are positioning one of the models. And I just want to point out the table that we're positioning it on has a round, well, a circular pad basically that is marked at every 10-degree interval. And so we've got some marks on that circle that allow us to carefully turn that model. It's the poor man's turntable that we use in this environment, but it does the trick. And so I'm going to go back further on now, and we'll start talking about the processing workflow that we used to convert the images that we're capturing with that careful camera work into a three-dimensional model. So the technology behind this, for us at least in the current iteration of our project, is we use a software called Agisoft Metashape. And this is a photogrammetry software that's designed to process images and produce these models. And it can be used for aerial imagery. It can be used for processing LiDAR point clouds, and it can be used for this close-in photogrammetry that we're using for the Ezell project. And the basic workflow that we follow is to import a set of source photos. We organize and then align those photos to create what's called a sparse cloud. Then we use the sparse cloud and the photos to build a denser cloud. This is a more dramatic processing step. And then we can convert those points into a mesh, generate a texture, and then export the model. And I'll talk a little bit about each one of these steps in turn. So first of all, this screen shows an example of images that have been collected for a set design called for the show, The Death of a Salesman. And in the image, you can see on the left-hand side in that little file window here, I've basically grouped photographs into 4 different groups. These are basically designed to model the 4 different heights that we set the camera to. So as we're capturing these photographs, the camera stays in one position. We rotate the model around through 360 degrees, taking a shot every 10 degrees. Then we come back, we move the camera up. do that again. And in this case, we've done that 4 different times. And so I've separated in the software the camera groups into 4 different groupings because of the different height of the camera for each one. And you can see in the image section, the blue squares represent the estimated camera position, because the software basically, when it builds this sparse cloud, it looks at all of the images and estimates a position where the camera was when it captured that picture. And so this generates a sparse point cloud, and you can see it in the center here. There's a little bit of a trackball that allows us to maneuver it around when the software is live. And this is just a screen capture of that. Whoops, I didn't mean to do that. No, let me get back to where I was talking. There we are. And so the sparse point cloud is created from that. And you'll see an example of one of the source images down here in the lower left-hand side of the screen. And that's just the image that corresponds to the red square that you see in the main screen. And so as you can see, we've got an even distribution of photographs around the model. We've got 4 different heights here. It gives us a very detailed view of that maquette from every possible angle. Now, once we generate the sparse cloud, and that process takes, 10 to 15 minutes or so to generate that, we can come back and then generate a dense point cloud. And you're seeing the results of that processing here in the right-hand side. And as you can see, we get a lot more detail. We've zoomed in using this study area box here to kind of define the region of interest for us in a little bit closer. And there's a couple of things to note about this. First of all, you can see there's some spurious points around. And when you build this dense point cloud, sometimes you get points that are associated with either objects in the background or just the fact that we've got overlapping photographs and there's noise in the system. We get these additional points that aren't necessarily a part of our model. And we'll talk more about that in a little bit. But on the left-hand side of that screen, you'll see a little bit of information about the metadata or the processing steps that were adopted in this particular run. Good grief, I keep doing that. So the thing I want to point out is we're using an ultra high quality setting. And in this case, I've got over 77 million points in this dense cloud. And the processing time involved with this, first of all, we build a depth map, and that took about 2 hours and used about 8 gigs or almost 9 gigabytes of memory. And then we processed the dense cloud generation from those depth maps, and that took over 10 hours. And the final size of the file is about 1 gigabyte. And so you can imagine this sort of work, it takes a computer that can handle that sort of processing and also the space to store these things. But the bottom line is we get a model of the dense point cloud that we can then use to create a mesh. And this is just a cleaned up version of the point cloud on the lower right. And so you can see some of the excess points have been removed. I've actually sliced off the bottom of the model where the turntable was shown. We don't need that for our final product. And you can see we get a pretty good representation of the features on the stage, the little figures that are there, and then of course all the areas of the stage. Around the edges, you can see there's a bit of white and black speckling. That's from a bit of uncertainty about that image. Don't know why I keep moving forward there. The image on the left, I did want to point this out. We are able to filter and symbolize these points based on a confidence level. And so the points that appear in many different photographs or that are generated from several photographs have a relatively high confidence. And then other things that might move around a little bit within different photos, basically because of the alignment of the photo may not be exactly perfect, will have a lower confidence level. And those are the red points that you see in that image. But the bottom line is we can generate from that dense point cloud a mesh, and that's what we're looking at here. So in this case, we've actually converted the point cloud, which is just a bunch of single point locations in space, into a triangulated irregular network, or a TIN. This is basically a mesh where all of the point objects that we had before have now been converted into nodes of a triangle. And so as those, in areas where we see a lot of detail, the nodes of those triangles are very close and the triangular faces are extremely small. And that's basically what we do to create the three-dimensional model. And this one shows the mesh with a color that's been extracted from the photographs. So we get the model was a grayscale model basically, and so we get an image here that looks very much like that. We can also look at it just in its natural state as a triangulated irregular network. And in this case, I've zoomed in on that red area in the main thing to show you that you can kind of see in this image, this is part of the girder structure, and you can see a very dense mesh here. And that's one of the things that we get from this model. When we build a very detailed point cloud, we get a very detailed mesh out of that. And that's one of the things that we need to resolve moving forward to basically make this project work a little bit better. Right now, we're getting very detailed models that may in fact include a little more detail than we want in certain areas and not as much detail as we need in others. But the bottom line is we get a three-dimensional model that we can now share using various methods. And one of those methods is using an application called SketchFab. And let me get to that. So facilitating access to this collection was one of the main reasons that we started this whole process. As you can imagine, from just simply looking at photographs of these models, you don't really get a sense for what's going on. And in fact, you're basically limited to the images that have been captured and the available angles that you have for viewing such things. And in that case, it may not be as compelling or as interesting to a user as it might be. And so interactive models are compelling, and they enable this free exploration. The user can actually pick up the model, move it around, and look at different angles. We also have the ability to add annotation, and that adds value and enables a deeper engagement. Academics can use that to share information about these models and to help the viewer understand what's going on at a deeper level. And of course, once we have created these models, we're conserving staff resources. Instead of having to set up a special exhibit or pull objects out of our storage area into an area that users could actually access them. In this case, we will be able to share access to these materials in a much easier fashion. And one of those potential options is the SketchFab platform. And SketchFab is a three-dimensional model sharing platform. It's based in the web, and users can set up an account and share models through it that allow people to interact with them. And I'm going to move forward here, and let's see if this is going to work. I'm going to have to stop sharing here for a second. And stop hold on a second. I'm not very good at juggling all of these screens. So let's see here. I need to get to SketchFab. Let me get this set up and I'll share my screen again. I'll be glad when we stop having to juggle screens and we can talk about things like this in person. So this is you should be seeing my browser screen now. This is the Death of a Salesman model that you've been viewing. And I'm going to pull this up in SketchFab. and open it up in full screen. So as you can see, I'm able to move the model around the screen. I can look at it from various angles. And as you can see, there are some imperfections in this model. These are things that we need to work out in our processing steps to better capture some of these areas. Actually, I think the capture is probably not the problem. It's more the processing of the images that don't necessarily give us all of the details that we'd like in our final model, even though they are captured well in our dense point cloud. But one of the other aspects of the SketchFab platform is the idea that we can build in annotations. And so as you can see, I've placed various annotations across the area here. And I'm just going to go to the first one here. The comments that you'll see in these annotations were provided by Rob Morgan. He is a professor in the fine arts department and is an accomplished set designer in his own right. And he is very familiar with the John Ezell collection. And he has generously provided the information that I'm showing in many of these annotations. So the interactive nature and the ability to share additional information is, I think, one of the true points where this sets it apart from just being able to look at a bunch of images, flat images, static images. So someone like Rob can share their knowledge and information about this. And in fact, we can look at it from several different standpoints. From the standpoint of understanding what the play itself was about, many of us are familiar with the story of Death of a Salesman, but this is about Willie Loman. He was a failed salesman, and he returns to his once proud home in New York City. And that's the setting for the play here. And so you'll see on the stage, we've got a figure that represents Willie Loman, and in the annotation, we can guide the viewer through several different annotations. The setting the stage annotation at the upper right basically talks about the setting for the play, but it also brings out some interesting points about the set design here. And so we've got at the middle of the stage, we've got the Loman house, but surrounding that, we've got all of this development and structures. And in Rob's comment, he states that it takes place in Brooklyn, New York, with the post-war population boom. The once open and natural Loman estate is being boxed in and drowned out by encroaching buildings that work as a metaphor for Willie Loman's current state of mind, lonely, confined, and ignored. And I think that sort of comment basically helps us understand that the stage is designed to reinforce that idea and to bring that home. And having the ability to add these annotations is a very powerful way of basically communicating that sort of information. So we've got the Loman home at the center. We've got the rear stage wall, and this is where we can get into another aspect of it that talks more about the technical aspects of putting on the show and designing the stage. In this case, we're talking about the plaster cyc or cyclorama that is the wall painted at the back of the stage. And there's several other annotations here. One of them, I was not aware of this, but these are called VOM exits at the front of the stage. And they allow the actors access and digress from the stage through the front. And then I added a couple of annotations of my own to talk about the model 3D production. And there are some incomplete objects. You'll notice here on the stage, the figures of Willie Loman and the two figures to the right are incomplete and not well articulated. And even though they were very present in the dense point cloud, in the conversion process to create our mesh, we're losing a bit of them. And that's mainly because these are very thin features. So they're basically cut out silhouettes that were positioned on the stage. And so they show up well in the images and the dense cloud, but when we create this mesh, we're losing a bit. And that really is something that requires additional processing to address. In contrast, the girder structures that we see here in the stage, in the rear of the stage, as you can see when I move the model around, are fairly well articulated, even though they're deep within the the stage area. And so, you can see when looking at it in this way, we're able to see areas where the modeling isn't doing so well, but we also get a pretty good view of this this superstructure in the back of the stage. So I really feel like this is a very interesting way to interact with these sorts of models, and it gives us a chance to share that additional information. So I'm going to stop sharing there, and I'm going to pause here for a moment. If anyone has any specific questions, or Rob, if you'd like to actually add any comments there, be happy to hear anything you'd like to say.
Sorry, I had to unmute myself. You did a great job, Bill. Fantastic work. I would only add that that particular theater, if our audience here are St. Louisans, is the Repertory Theater of St. Louis. And I both went to undergraduate school at Webster in that and designed a lot in that space. So John quite often did what are called co-productions between the Repertory Theater of St. Louis and Cincinnati Playhouse in the Park. Both theaters are thrust spaces, meaning there's audience on three sides, much like Florida. There's water around Florida. There's audience on three sides of a thrust space. And Cincinnati and Repertory Theater St. Louis have very similar plan views. And so a show might be built in St. Louis and sent to Cincinnati or vice versa. But John Ezell himself is a mentor of mine and a bit of a legend.
Excellent. Thanks, Rob. Yeah, and just so you are all aware that the goal of the project that as we are working on it right now is to devise a consistent workflow for converting the collection of objects that we have, sitting in a vault in the library into something that we can publicly share. SketchFab may or may not turn out to be the best mechanism for that. There are other potential platforms that we might want to investigate. And, we've got issues of, protecting intellectual property and things like that, that we need to work out. But the ultimate goal is, this pilot project is designed to figure out how to do this and do it well. And then we'll move on from there to see what we can do with it. But I wanted to give you all a bit of an experience, and I didn't notice any other questions, so I'm going to keep moving along. Unless if you do have a question, please feel free to unmute or enter it into the chat, and we'd be happy to address anything specific that you'd like to talk about.
Hi, Bill.
Hey, June.
Yeah, it's really nice models, but I have a question like follows noise in your mesh points. How much manual work you need to be involved to remove those points, remove those noise to build the 3D thing?
Yeah, that's an excellent question, and in fact, that's a work in progress. The initial model that I showed had, you could see there were some extra points on the outside of the model. Those are relatively easy to remove because you can just, well, relatively easy means you can manually select them and delete them. Whereas in in areas on the back of the model, for instance, where we have a large flat panel and not really much going on, I would love to simplify that. And I'm working on a process to make that happen. I think there are tools for simplifying the mesh. You can easily just de-densify the mesh. And that's certainly one way to deal with it, but it's a little less, I guess it's a little less specific, and there's less control. You just de-densify the whole thing. And so I'm looking for ways to identify maybe the corner points on the back panel and then replace the mesh with a single flat polygon, which would obviously cut down the size of the model itself, remove a fairly large amount of the facets of that tin, and make it a lot more manageable as far as sharing. But I don't have a good answer for that yet. It's something I'm working on. Do you have any suggestions?
Yeah, so I'm just curious, for example, the whole project is kind of like 100% of time. And when you remove those manual work to remove those points, it's kind of like a statistically, like how much percent do you have an approximation? Like is that the most time-consuming part, or most pain part to make the model look better?
Agreed, and I think ultimately there's going to be a trade-off probably.
Uh-huh.
I can say I've got a meeting with a professor from computer science next week, and I'm hoping he's an image processing expert, and so I'm hoping that he might have some suggestions that might help us, facilitate this process a little bit. I mean, I would really not want to lose the detail that we're seeing
Uh-huh.
on the stage, because there's a lot of interesting intricacies that are articulated there that we don't want to lose. And so it's going to be, it'll be interesting to see how much time we need to invest to create a
Uh-huh.
good model. And this also brings in the idea of preservation and the
Yes, right.
balance between providing access to a model that is educationally sound and of value versus preserving something in its original state.
Details.
And so I think there's a question to be had there about how do we balance that? How much effort do we need to put into the capture, well, not the capture, but the processing in order to get to our final goals. Ian, do you want to say anything about that? Is that, I mean, you're a preservationist, so.
Well, I also want to add that we're looking into ways to automate masking out unimportant information in Photoshop, which again, like, is simple enough to do manually, but we're talking about a lot of images. So it's kind of a weighing out. You can tell Photoshop to do a lot of automated things, and you can get a variety of results from adjusting those parameters. But we're trying to kind of zero in on the balance between how much information we feed the software to get a usable result. And because like Bill said, the processing takes some time. So we're still figuring out, we may be giving it way too many images than we really need to. We kind of want to err on the side of having more information than we need for the sake of detail, but for the sake of streamlining these processes, we may find that we need many fewer images and to get a usable result. But yeah, again, as you were talking about, a preservation copy versus an access copy, these things are really easy to determine with a single digital image, but we're kind of, as Jennifer talked about with her CS3DP talk earlier, I would assume we're making the rules as we go for this type of data. As far as what a preservation copy is and what an access copy is. So, yeah.
And I think ultimately it's going to come down to the idea of what is the ultimate goal for the object that we're trying to create. I do see a question from Rick. The discussion so far is focused on surfaces. Will your process also include accurate color capture in the resulting models? And yes, Rick, actually, I guess I probably might not have picked the best model to use as an example, because that model was actually a grayscale a non-colored model, basically, but we are able to capture color, and in fact it's part of the photographs. And the last processing step, where we convert the mesh into a 3D model, actually captures from the original photographs, it captures a color to assign to each one of the facets. And so the color is actually accurate to the original model. And after the demo, I can actually show you another model that we have in SketchFab that has some color associated. The model that Ian showed in his original slides about the Ezell collection actually is colored, and we were able to capture that color. So it is part of the process. Now, if there are no other questions, I'm going to go ahead and start with the hands-on demo, and I shared at the beginning a link to the box folder that has the materials. If you haven't had a chance to download it, I encourage you to, but I'm not gonna pause to give time for that. I want to go ahead and keep moving. So I'm going to share my second screen again. And now I'm not going to go into the slideshow because I just want to cover a couple of these slides. First of all, the demonstration I want to go through today uses a software called Regard 3D. And Regard 3D is an open source photogrammetry software, and it's not actually that bad considering the fact that it's free, and it's relatively easy to install. It has a Macintosh and a Windows version, and so the box folder has an install file for Mac, which is the .dmg file, and then the .exe file is the install for Windows. So depending on what system you're using, the install should run pretty quickly, less than a couple of minutes, I think. But if you'll download and install Regard 3D, I'll talk briefly about that package. So the package itself, as I said, is an open source set of basically algorithms that are used to create surfaces from imagery. And the homepage for Regard 3D gives a lot more information about that and excuse me, and the underlying algorithms that are used by the software. And I'm not going to go into that level of detail. We're basically going to use this tool and not really talk about too much about what's under the hood. But there is a lot of information on the homepage, and there are a set of tutorials that would help you with other aspects of the processing if you so desire. Now, one part of this that we're not going to demonstrate today is the cleaning of the actual model. And for that, I've used Metashape, but I'm not sure yet if that's the best tool for the job. And I'll talk a little bit about that at the end of the demonstration. But just briefly to talk about what we're going to do, the source photos that were included in the box folder are 9 photographs of this bust of Seneca. And this is just some standard photographs that were taken with a handheld camera. I have a feeling it was probably a smartphone or something like that. And so there's not a serious and there's nothing magic about these photographs. I found the set on Flickr, downloaded them, and installed or included those in the box folder. So if you will, just go ahead and open up Regard 3D, and we're going to start a new project. So the Create New Project button up here at the upper left allows us to set a project path. I'm just going to use my desktop, because I've got on the desktop a folder for these downloads of Intro to Photogrammetry. I'm going to use that as my folder for the project, and I'm just going to call this Demo. And now the first thing you do in a project like this is import the photographs. And so on the left-hand panel, you'll see an Add Picture Set button. And that allows us to add the files. And I'll just browse into the folder that I downloaded, and I should have extracted these files, and I didn't. So give me just 1 second. If you were like me and forgot to extract the folder, you'll have to do that really quickly, and it shouldn't take very long. So just unzip the file here, and we'll get a folder that includes our images. And we'll look at those once we bring them into the application. So for the picture set, I'm going to use the folder and just click and shift click to select all of the photographs open those, and you'll notice as it populates the window here, it looks like this was a handheld digital camera, a Canon model. And so there's extra image, or I'm sorry, there's extra information or metadata that comes with the photographs. And in this case, it shows the size of the picture, the camera that was used, and the camera model in this case is something that aligns with the underlying software, and it has an understanding of the focal length and the sensor width and so forth of that particular camera model. There are ways for software like this to import information about the cameras, and that's an important aspect of making sure that the system works well with the photographs that we're using. Now, this set of images doesn't have GPS, but it does have that functionality in here to read geographic coordinates from those images. So now I'm just going to look at my picture set, and if I double click, you can see I get a image of what the pictures look like, and they're, you know, just standard shots of the bust that has been captured at several different angles. And we're going to use those as our source photographs. So the next step of the process is we compute matches. And this basically gives us our the ability to create key points in each one of the images and then match those points with key points in other images. I'm not going to change any of the defaults here, but you can see there are a lot of different settings that could be used to optimize this process. And in fact, they've got a few different algorithms that they use, not only for key point detection, but for the matching algorithm. And I'm not familiar with the differences between these, but they obviously give you different functionalities. So we'll go ahead and run that. And now it's basically computing all those tie points and matches between the images. And this should take less than 30 seconds or so to run. If it takes a little bit longer on your system, I will point out that the folder that you downloaded includes a Word document that drives you through the steps that we're doing in this example. So if you need to finish this offline, you'll have the materials that you'll be able to do that. So this took about 18 seconds to make that process. We've got 1,500 key points per image, average of 2,400. So there's a lot of different points that have been associated with each one of these images. So I'll click OK there. And then I just want to have a look at my matching results. So under the Show Matching Results option, we get a new window that allows us to view the key points and the matches. And so I'm just going to start up here at the key point option. I'll show all of those, and you can't really see them on this presentation, but in the preview window, you'll get a very detailed view of the bust itself and the key points that have been found. And I'm just going to focus in on the face area here. And so you can see the circles that have been defined here all represent a key point. The size of the circle is associated with the size of the point that's been identified. So the smaller points are pinpoint locations that have been matched in several photographs. And then the symbols also have, if I can focus properly, the symbols also have a little line associated with them, and that indicates the direction in which the key point is facing. I'm going to close that window. And now let's go ahead and look at the lower frame, and that shows us our matches. So this shows two photographs side by side, and it links up the key points on one photograph to the same key point in another photograph. And this just gives you an option to view these pairs and understand how well connected that they are. So you can get a sense for, you know, what sort of matching has been done and so forth. So we can close that window. And now the next step is to create our sparse point cloud. So we've done our matching, but now we need to, we're going to do the structure from motion process to identify where our cameras are and to begin building the point cloud that we want to create out of this process. So we'll run that, and this triangulation process will take a little bit longer. And of course, this is all tied to the processing capabilities of your particular system. It didn't take very long on mine. And I'm going to increase the point size here. And you can see the little trackball has these white lines that allow you to kind of drag and move it. And you'll see here in the image, I've got green dots. They correspond to the locations that have been estimated for each one of the photographs. So the photographs are all lined up, and then the head itself, or the bust, let me rotate it around here. Whoops. When I zoom in, you can kind of get the sense of the bust here, but this is a sparse cloud. So the point is not to accurately reproduce it, but the point here is to identify where those cameras are. And so we're kind of getting this sense for the distribution of the cameras that were used to capture the photographs. And as long as we like this, then we can move on to the part where we're going to create our dense point cloud. And so this is the densification process. And we start with this create dense point cloud. And in here, we've got even more options. So there's several different densification methods that we can apply. We can use different settings for the sensitivity and so forth. I'm just going to leave this all set up at the default level. Click OK. And this is the longest part of the process. And so this can take up to a minute or so. And while that's running, I'm just going to pause for a second. Does anyone have any questions? Okay. Well, we're going to watch this run. This is exciting, huh? I can hardly wait. Although I've seen this show before, so I think I know how it's going to turn out.
Bill, I have kind of a dumb question.
Sure.
Let's say I would like to make a 3D model of an object. I don't know, maybe this baseball or something. What is there a rule of thumb for how many photos I should take?
Yeah, that's an excellent question. I mean, the thing that we're going to notice in this model is that we don't have enough. And so I think actually I'm going to lob this question over to Ian, because he's the photographer amongst us. So Ian, why don't you take a stab at that one?
Well, the more images, the better. I've found I've just started to do photogrammetry with the drone that I have, and with that, it's easy to automate. I can set it to take a photo every few seconds and then just fly it around, and it does its thing. I feed it in to the software. If you're moving around an object, obviously it takes a little more effort to get each image. But it definitely depends on the complexity of the object. I've found, like, for instance, the models that we're shooting, the Ezell models, the back is just a flat surface. We could get away with, a couple images to render the back of those models because it's a flat piece of foam core. But then, the areas where we're having trouble getting detail in kind of the shadows in the back, the little nooks and crannies, it pays off to pay more attention to those areas. So you can kind of intuitively know where you need to give more attention to your data capture. But I mean, I would be interested to see the absolute minimum that you would need for a sphere, like a baseball with a simple texture. My inclination is that you could get a model with 6 photos. It may not be a perfect sphere, but I'd be curious to see what you would get from this particular software. But really, it comes down to balancing. It's really not hard to feed lots and lots of data into the program, but it will take that much longer to get your results. So it's kind of a balance between those two factors.
Thank you.
Yeah, I second that emotion because I think that there is going to be a trade-off at some point where the extra photos are just going to bog down the processing. Um, so it looks like our model is done, and I'm going to turn this around and have a look at him. There he is. Whoops, that might be a little too close. So here is Seneca, and whoops, sorry, my mouse is a little jumpy. We've now converted our sparse cloud into a dense point cloud, and I'm going to close down the size of those points a little bit and just zoom in a bit if I can do it without going too far. So you can see we still got a little bit of gap. The blue, speckling that we see here are basically gaps in the model where there's space between the holes. And so that's going to be alleviated when we create our mesh, because those spaces are going to be filled in with triangular facets. And then we'll assign colors from the images into those areas. The other thing I want to point out is you can see now we've got these extra lines of points in the model because of the background that was in those photographs. And so if you recall, there were some columnar structures behind the bust that are basically causing us some issues. And there is some tools that you can use to mask out that background. But the other thing I'll point out is if we turn him around, we can see that there's nothing in the back. And so we're basically, because of the lack of photographs behind the object, we're missing, details there. And so this is a good example of a little bit too few photographs in that we're not capturing areas of interest. And I would point out the area below his chin where we have this hole here is due to the fact that we may only have one photograph that or maybe one or two that actually capture that area well. And so designing your strategy for capturing photos is an important aspect of all of this. So now we've got a dense point cloud. Let's convert that into a surface. And I'm just going to create the surface, and we'll use all the defaults here. And this is now building that mesh product. So we're combining or linking all of the points. And this is where things can get a little interesting. And I think this is where some of the translation from the dense point cloud to the surface on the Ezell models is not turning out as well because of the like the thin features on the stage are not working out so well because maybe the points are not being identified as being part of a flat plane. And I think that's an algorithmic thing, and I haven't had a chance to really experiment too deeply with that. But now we'll have a look at our surface, and you can see all of those background features have now been kind of combined into a more surface-like feature, and there's no holes anymore, but we've also got these objects, and we've got a flat plane around the back of the head. But if we turn farther around, we see that we've still got empty space back there. And so this is the kind of feature that would then be exported for use in a tool that might help us remove some of these excess polygons. And Meshlab is a tool that is capable of doing that. Blender also has some functions there, but that's an application I haven't worked with that much. It is also an open source application though. And so it would allow us to clean these things up. If we look in fairly close, I don't think we're going to see many holes anymore, even in areas where we had holes before. And you can see even this area under the chin is not only filled in, but it's also filled in with colors. So we've got not just a hole that's been covered with a single area, but it's articulated fairly well. And there is a range of color there that's basically captured from the photographs. And so the individual pixel locations on the photograph color is extracted, in many cases when you've got several different views of the same pixel, the system has to decide, well, am I going to average all those color values? Am I going to use the highest, the lowest, something like that? And I think that would tend to shift the color maybe in some way, and there may be ways to identify which particular photographs would be more useful for that. And I think also the points that Ian made earlier about consistent lighting are very important, because you want to have that consistent coloration so that even if you're using pixels from different photographs, they end up having the same color values.
And to address a question in the chat from Sean, he asked, is it helpful to zoom in and capture details without having the entire object in the shot? And absolutely it is. When I've made models of, and it seems like one of the main commercial uses for ortho photos and photogrammetry with drones is for construction sites. And with a large site like that, you generally do not have the entire site in a single shot. You're flying a drone maybe 50 feet over the surface, shooting down, and just getting lots of overlap between consecutive shots, but usually no overlap of all the images. And with an object like this, you can absolutely zoom into those kind of trouble areas, but the one thing that you have to worry about is depth of field. So the closer you get to an object, the shallower the depth of field gets. So you don't want to get so close that you have a lot of out of focus areas, because that will confuse the software. I mean, and that's, you could, even if you had a shallow depth of field image, you could mask out those out of focus areas and just feed in the sharp bits that you have, and the software will use that. It will recognize that as long as there's enough overlap with other images.
Yeah, and that overlap is a key point, because as Alex mentioned in his talk yesterday, when you're doing drone collection like that, you want to not only overlap side to side, but overlap front to back too. And I think he was arguing that a standard rule of thumb is to look for 70% side lap and about 30% front and back lap. And so, when you're designing to capture from a platform like that, you definitely need to be concerned about that overlap. When we're capturing here, we're turning 10% or 10 degrees every time. And so we get, very even coverage. And I think we get to see what's behind. Now, I did notice another question. Rick wondered about the landscape nature of one of the photographs. And no, I don't think that matters, because the software seems to be able to deal with that, at least from the standpoint of the Regard 3D option. We haven't tested this in Metashape, but I don't think we would have an issue there. Let's see then. June says, what's the difference between Regard 3D and Mesh 3D tools? Are you referring, June, to Mesh Lab?
Yeah, I probably said the wrong thing.
Yeah, that's okay. Yeah, Regard 3D it handles the photogrammetry. So it allows you to create the 3D model, but Mesh Lab is more of a mesh editing software. And so it is optimized for selecting polygons, de-densifying a mesh. It's got a lot of very complex tools that help you, deal with technical issues with the mesh, as in, the manifold edges and the orientation of each one of these cells has a normal that defines its directionality, and that can sometimes be turned around. And Mesh Lab has tools that allow you to address those sorts of issues. And so, Rick, I think you're following up again. The tool automatically deals with rotation of view, and I think that's correct. Yeah. Well, and with that, I'm going to stop sharing, because that is the, actually, no, I'm going to start sharing again, because I wanted to show you the other model. So give me a second. Let me get back to that. So we do have another model in our repertoire here. This is Dancing Aglugnasa, and this is the one that has color already in it. And so I just wanted to point that out. And this one, in fact, I hate to admit this to the crowd, but as you can see here, we've got really good rendering of the flat feature on the stage. And the stage furniture and things like that. I mean, this is the model I should have been using, but I was really interested in Rob's comments about Death of a Salesman, and so we stuck with that. But you can kind of see there's this hanging feature above the stage here that's fairly well articulated. And even though it's basically hanging out in there in space, and I'm going to have to go back to my notes and really look at the processing workflow that I used to generate this model, because it did a pretty good job, especially in this instance where it's captured this flat feature. And even the legs on the table are well articulated. Whoops, I even annotated that. I was so impressed with it. The one thing that isn't well done here is the back panel in the stage itself, and this whole area here on the left-hand side is basically a bunch of switchgrass or some type of vegetation that was very detailed and isn't well captured in this model. And in fact, we also in this one, we lost the entire back panel of the stage. This should be a flat panel here, and for some reason it's not being articulated in the mesh model, and I'm not clear on what's going on with that. So there are clearly some other issues we need to work out with this whole process, but I can tell you it's been very interesting, and I think ultimately we're going to solve these problems. Just working through them is going to be very interesting.
And I'll add, the goal for us with the capture is to create standards so the student workers can do this for us, basically. And so we're capturing every model the same. And to get the absolute greatest detail, that's one of the challenges I'm having with developing these standards, because a lot of it is just intuitive and like, okay, this looks to me like it's going to be a tricky area. We should get in closer right here, get some more detail, maybe make sure that we get more light in this area. But the way we've operated so far is just doing everything all the same, which may not be the best way to create the absolute best models.
Okay, and I just responded to your question, Rob, about the Seneca model. I did edit, I have a version of that where I edited out some of that excess stuff, and clipping those polygons was something I did in MeshLab. SketchFab does have some tools for that though, and I haven't yet gotten to the point where I've worked with those. And there is a question from Sidipto. Have you compared with commercial software such as Polycam that you can get on the iPhone App Store with your set of photos? Looks like your focus rightfully is on the correct way to capture the image. Yeah, actually, I haven't tried Polycam. I have an iPhone 12 that I'd specifically purchased so I would get the onboard LiDAR sensor. And unfortunately, life has conspired to keep me from playing around with that toy too much at this point. But at some point, I'm going to try it to see if that would help. And I know there are several apps for the iPhone that take advantage of that sensor and build models. And it does also photos as well. Yeah. Yeah, I'll have to check that out. Thanks for the tip. Okay, and with that, if there are no other questions, I will, first of all, thank you all for joining us late on a Friday afternoon. I really appreciate your attention, and I appreciate the contributions, Rob. That was excellent to have you here. Appreciate that. My colleague Ian and I, we both are happy that you have joined us. Hopefully you it has piqued your interest in photogrammetry. If you have further questions, Data Services is always here, and we are glad to help with questions such as these. So anyway, thanks for coming and have a great weekend.
Thanks, everybody.